Hello everyone, this is Flying Freak. Today we're going to talk about an elliptic orbit. That is right, we're going to talk about elliptic orbit. But before we talk about an elliptic orbit, I want to talk about energy. That's right, energy. There's different kind of orbits. There are the circular orbits, and we have the elliptical orbit, and we have the parabolic orbit, and we have the hyperbolic orbit. And one thing that I want to say is energy. This is how you write energy in astronautics. Um, and different orbits have different energies. And I kind of make this kind of joke with my friends, saying when I'm feeling down and kind of lethargic, I would say today I'm having a elliptic energy or a circular orbit energy. The reason is, you guessed it right, because the sign of the energy of the circular orbit or the elliptical orbit is negative. It can never be positive or zero. It's always negative. Then let's talk about the energy of a parabolic orbit. The energy for the parabolic orbit is zero. So this is technically the transition orbit. We're transitioning from negative to what? When you see any graph, well, probably not any graph, but when you see like a trend going from negative to a zero, the next thing that you would expect is to be positive. So again, the hyperbolic orbit has the energy of positive. So when I'm feeling happy and I'm energetic, I would say, hey, my energy today is the hyperbolic orbit. And, people in aerospace engineering would know what you're talking about. So let's get back onto track. We're going to talk about the elliptical orbit. The first thing we want to talk about is the geometry of it. Geometry, that is right. So I'm not a professional artist, so my ellipse will not look very pretty. But the first thing I would do is I will draw Earth, our mighty Earth, and I'm going to draw a focal point here and focal point here, and going to draw center line, center dashed line probably, and you'll see what's happening here. So I'm gonna draw the edge here, and I'm gonna mark my vertical edges, and I'm gonna draw a line. So it's kind of a ellipse. It's coming together. Now, everyone, just ignore the fact that this looks like a potato or a sweet potato, but we have a center here, and we have to draw a center horizontal line. And again, the circle right here, this is Earth. When you're studying astronautics, you feel very small because billions of people and billions of animals that live on this planet can be explained in this 2 centimeter circle. But anyhow, let's be real here. So this horizontal line is called the major axis. The major axis. Maybe it's called the major axis because it's longer, it's larger. And the vertical line here is called the minor axis. Okay, and all this terminology is important because in the future we will continue to use these terminologies, and if you don't know these terminologies, you will be struggling. So pay attention. Now, the first thing that I want to draw is a vertical line that goes from the major axis to the orbit. And this distance right here is called P. What does P stand for? P stands for Semilatus Rectum. Semilatus Rectum. That is I, but that's so this is Semilatus, sorry, and rectum. Jeez, I can't write today. Semilatus rectum. Right, and you might be wondering, okay, is this distance same as this distance here? And yes, you are right. So this distance right here is same as this distance. So since that's done, we're going to talk about another parameter. Let's talk about the semi-major axis, shouldn't we? The semi-major axis is the distance from the center to the edge of the orbit. So it would be here. It's in blue, right here. Denoted as A. It's called A. And this is called semi-major axis. Or just semi-major, it doesn't really matter. And the next thing we are going to denote is in yellow, from the center of the orbit to the focal point. And we denote that with C. That is called just distance between focal point 1 to the center of the orbit. There's no really name for it. So I'll write it down on the left side. C is the distance from center of orbit to F1, focal point 1. And F1 is obviously here. And F2 is here. Okay, now that is done, let's talk about the semi-minor axis. What do you think semi-minor axis would be? If you guessed that semi-minor axis is here, you are correct. This is in fact semi-minor axis. Semi-minor axis. And actually, for the semi-major axis, this distance is also actually a semi-major axis. So using this triangle, we can make a relationship. What kind of relationship can we make? Well, we clearly know what Pythagorean theory is, right? So it's a squared equals b squared plus c squared. So this relationship will be very important in the future, or in the near future. P is just angular momentum squared over mu. This is the standard gravitational parameter of E because we're talking about Earth. And what is the standard gravitational parameter of Earth? That's right. If you said it was 3.986 times 10 to the 5 kilometer cubed over, what is it? What is it? Google it. Google it, okay? Google it. Next time I'm going to ask you a question, okay? Hey, I'm just kidding. It's second squared. So, since we talked about geometry, we actually forgot one thing. I want to, this is probably one of the most important thing. What do we call this point right here? We call this point the periapsis, or the perigee. P-E-R-I-G-E-E. What do we call this point right here? The furthest point from the opposite side of periapsis. So periapsis is the point that's closest to the Earth. And this point right here is called the apoapsis. Or you can note this as apogee. And this is the point that is furthest away from Earth. Nice to know these points because in the future we're going to denote geometric relationships by stating this is RA, distance from the Earth to apogee, and this distance is RP, distance from Earth, center of the Earth, to periapsis. So did you write all this down on your notes? Because I'm going to erase this page. Okay. In fact, I want to go back. Sorry. And I want to denote some angles, some true anomaly angles. So this is theta 0, and this is theta equals pi over 2, and this is theta equals pi. This is theta equals 3 pi over 2, and what can it be in a negative value? That's right, it could be negative pi over 2. And of course, this could be, pi theta equals to 2 pi and something like that. But yeah, I just wanted to say that, and we will move. Like I said, sorry about that. We are going to talk about the eccentricity. Eccentricity. How much of an elliptical characteristic does an orbit have? Eccentricity is denoted as E, and this can easily be said that E equals C over A. What happens when A and C is the same? When A and C is the same, it's actually a circular orbit. But the thing is, for an elliptical orbit, E is always less than 1 and it's always greater than 0. So for a circular orbit, although we're not talking about circular orbit today, for circular orbit, E is actually 0. So anyways, our eccentricity is C over A. The reason why it's always between 0 and 1 is because C is always less than A. If you look at your geometry on your notes, you can see that semi-major axis is always larger than semi-minor axis. The next thing that I want to talk about is P. There are different ways that we can represent P. And what did I say P was? It's Semilatus Rectum. So P, Semilatus Rectum. I have to connect these two. Semilatus Rectum. And P is A, which is the semi-minor axis, 1 minus E squared. What else can P be represented into? Well, P can be used with, H squared over mu of E, depending on what kind of planet you're orbiting, right? So if you have an elliptical orbit with Mars, then your P is going to be H squared over mu of Mars. And mu of Mars, which is again the standard gravitational parameter of Mars, is not the same as Earth. The most important way of representing P is to relate P with trajectory equation. Trajectory equation is R equals P over 1 plus E cosine theta. E is eccentricity, theta is true anomaly, R is the distance from the center of the planet to the spacecraft. That means P is R times 1 plus E cosine theta. Let's talk about how we can determine the velocity of the spacecraft in different positions of the orbit. So for example, if a spacecraft is orbiting, is the distant velocity at position A same as distance at position B? No, it's not. I should probably denote it as this. So VA is not same as VB. Why is that? Because the closer you are to the planet, the faster you go. And the further you are, the slower you go. And why is that? because the angular momentum is constant. So h, well, I should probably say h is constant. And what is h? H is simply r cross v. It's probably like this, because cross gives you vector. Cross gives you vector. What does a dot product give you? It gives you scalar, right? So if you do this, then this is h. But yeah, angular momentum is conserved. Therefore, velocity at A is faster than velocity at B. How do you find that out? How do you find a velocity? You use energy equation. Again, energy is written like this. If I write it better, it's like this. Energy, and this is applicable to all orbits, is velocity squared over 2. What does this look like? This is the kinetic energy, right? Minus mu over r. Minus mu over r, this is the potential energy. And you might be wondering, why is it negative? Doesn't potential energy go up with the radius? Well, let me show you. So potential energy. Let me erase this page quickly and rewrite it. Equals v squared over 2 minus mu over r. Right. So mu over r actually has a graph like this. So as r goes up, our negative mu over r goes to 0. What happens if r goes down? Well, our potential energy goes down because our negative mu over r, magnitude of it goes up, right? As we can see, it's going downwards. The magnitude is going up. So the maximum potential energy is 0, but obviously we can't reach the theoretical value of 0. So this is our energy equation for all orbits, applicable to all orbits. All right. Well, if we have this, can we find velocity? How many unknowns do we have? There's a lot of unknowns. We don't know what energy is. We don't know what velocity is. We know what mu is. We don't know what the radius is. But what if we do know what the radius is? We know what the radius is because we have this equation. And this is simply values from the geometry of the orbit, right? Velocity is not the value from geometry of the orbit. However, p, e, theta, they are all from the geometry. Okay. There's one more equation that I want to tell you, which will complete the frustration. Energy is negative mu over 2a. 2a is also known because it's from the geometry, and mu is also known because we know what planet we are orbiting. It's the mu e. So we know energy. So I'll circle that in red. We know energy because we know the standard gravitational parameter of the Earth. We know the semi-major axis of the Earth. We know the radius that the spacecraft is at. We know this. So the only unknown that we have is the velocity. So we all can do that, right? But for those who can't, I will do it with you. So it's v squared over 2 equals to negative mu e over 2a plus mu over r. Now we multiply 2 on both sides. And we can cancel it, and we can square root both sides. Like this, and our velocity is that. Boom. So we can find velocity at any radius of the distance from the center of the Earth to the spacecraft. For example, spacecraft is here, our R is R1, and we can find the velocity there, velocity at 1. However, if we're looking at trying to find a velocity at 2, at R2, well, we can still find that as well using this majestical equation. So if you enjoyed this video, click that subscribe button and click that like button as well, and I'll see you guys in the next video.